Greetings, everybody. So, on this video, we are going to discuss observer design for nonlinear descriptor systems. So, we are presenting the results of a recent review article that was published in Circuit Systems and Signal Processing. This happens to be open access, so I'm going to put a link in the description of the video, and you can download it. And if you have any questions about the article, feel free to leave a comment in the comment section. Okay. So, we are going to discuss about observer design. So let's begin by talking about systems. So let's say we have a system right here. Of course, how is the system described? It is described by a series of differential equations. Okay, so let's assume that we know the differential equations of the system. Okay, the system, as you know from state space theory, if you have had a course on control systems, it has a series of states. These states may be representing the internal variables of the system: temperature, pressure, displacement, velocity, whatever. Okay, so uh, all of these states we probably don't have access to. What we do have access is some information about the states through the system's output. So the output is generally considered some sort of linear combination of the states. So let's generally assume that we know some of the states, but not all of them. Okay. And usually the system is subject to some sort of input. Okay. We can generally assume that we know also the input as well, but there are cases where we actually don't even know the input of the system. This is the case where we have some unknown inputs. Okay. So we have a system where we know the differential equations of the system, we know the input to the system, we know the output to the system, and we know some information about the states. Okay, so the states are generally unknown, but we have some information for them through the output. Okay, so the goal of the observer is basically to try and estimate the internal information for the system, okay, the internal states, the things that we cannot directly measure. Let me give you an example. This is a very classic system. Consider a system with many masses. In the figure, you see just some two masses, but we may have three, four, five masses, whatever, interconnected. Okay, this is a classic spring mass damper system that can model the damper system of a car. It can actually model different floors in a building and how they oscillate. Okay, so assume that for the final mass, we actually have some sort of infrared and we actually measure the displacement for the final mass. Okay. This system is described by a series of differential equations, and we can only measure the displacement of the final mass. So we have some information about the system, but we are also lacking a lot of information. So we don't know information about the velocity of the second mass, and also for the first mass, we don't know anything. We don't know its displacement, and we don't know its velocity as well. So that's a classic observer problem. By having some information, we only know the final, not the final, sorry, we only know the displacement for one mass, and we also want to learn information about the other masses that we cannot directly measure. That's a problem for an observer. Okay. Again, consider another problem where we have multiple tanks filled with some liquid, let's say water, and they are interconnected, and we have some valve control. So we know the differential equations that describe the interconnection for these tanks, but let's say we have again some infrared and we can only measure the level in a single tank. Okay, let's say we have three tanks, we can only measure the level in the first tank. We cannot measure the level in the second and third tanks, but we know the differential equations that describe the interconnections. So this is a classic problem again for an observer. We know partial information for the internal states, but we need to estimate the other states as well. Okay, so that's the observer problem. That's what the observer does. Okay, I have a graph right here showing this. So the observer is a secondary system. Basically, it's again a set of differential equations. Okay, we usually simulate it in a digital computer. Okay, so it's not a physical system. We may have the original system, which is a physical, mechanical, or whatever system, but the observer is usually just an artificial system. So a set of differential equations simulated digitally. Okay, the observer takes some information from the original input, if we know it, and from the output of the system, and manages, ideally, to estimate the internal states, the states that we cannot directly measure. Okay, so this is an example here. I have the Lorentz system as the master system, The output is a linear combination of the states from the Lorentz system. The observer gets this information and manages to estimate, I'm sorry, the internal states. See the graph here in a larger figure. So here the red, green, and blue trajectories are the trajectories of the original system. Okay. The black trajectories are the trajectories of the observer. And you see that for the first 70 seconds, they are completely different. So initially the observer starts, and because I don't have a feedback term, the observer fails to estimate the original states. Okay, so basically it doesn't provide us any information about the original system. At 70 seconds, what I do, I actually, uh, you know, um, click a switch inside the observer, and the observer starts working. And immediately after just 1 or 2 seconds, the black curve, which is the estimation, falls right on the original state, which tells us that after 70 seconds, when I switch on the observer actually manages to estimate the internal states of the system. Okay, so that's what ideally an observer should do, if of course designed correctly. This is again another simulation from another nonlinear system that I had. If you see, the original states are in blue and the red are the estimated states. And you see, for example, for the fourth state right here, the observer starts from a wrong estimation, and after 10, 11, 12, 15, 20 seconds, the estimation begins to converge correctly into the original state. And of course, this happens for all states, x1, x2, x3, x4. The observer, after 5, 10, 15 seconds, estimates correctly the internal states of the system. Okay, and this happens from partial information. Okay, so what we did in our paper. In our paper, we studied a much more general category of systems, the systems called descriptor systems. I don't know if you have heard about them, probably not in an undergraduate course because they are more advanced topic. Descriptor systems are also termed singular systems or DAEs, differential algebraic equations, or generalized state space systems. Their difference is basically that we have a matrix epsilon here, and this matrix epsilon is non-invertible. And basically what it does, it symbolizes that this system is described by a series of differential equations and and algebraic equations, I'm sorry. Okay, so we have a collection of differential equations and a collection of algebraic equations. Algebraic equations means that there are no derivatives inside, okay? This is a much larger category of systems. It can model a much larger family of systems, but actually their analysis and control is much more difficult. Okay. Moreover, we consider not only descriptor systems, but nonlinear descriptor systems. So, both the state equations and the output equations have a nonlinear function f or g right here. Okay, so f and g here are nonlinear. Okay, so by the way, this analysis becomes much more difficult. And also, let me note this, the nonlinearity in the output is something that has not been very common in previous years. I think it has become much more common in the last 10 years or so. Of course, nonlinearity in the output makes the analysis much more difficult, but it's very useful. It's much more difficult, of course. It's very general, and there have been papers where they point out that in practice, there may be nonlinearities in the output. I think they had some examples of robotic systems, if I remember correctly. Okay, so this is a very big category of systems. And we studied how many publications have been published in the topic of observer design and under what conditions. So basically in observer design, if you're familiar with state space, for descriptor systems, the idea is pretty much the same. What we're trying to do is derive a linear matrix inequality, an LMI, and if we find the solution of the LMI, we actually have the feasibility of the observer. Okay, we find some feedback matrices for the observer through the LMI. Now, the way that the LMI is structured has to do with what sort of nonlinearity we have in the system, the f and g functions, okay? Because the idea is this, when deriving the nonlinear function, when deriving the LMI, what we need to know about the nonlinear function basically is some sort of way to bound the function, okay? So by knowing how we can have a bound for this nonlinear function, we can actually discard it in the process of creating the Lyapunov function and the LMI. And instead of the nonlinear function inside the LMI, the resulting LMI, basically we have some sort of term, let's say general, some term that has to do with the bound of this function. Okay, I'm describing this in a very general way. If you read the papers, you will understand what I mean. Okay, so the type of the nonlinear function will change the final LMI for the observer design. Okay, and here I have a collection of nonlinearities that are the most common in practice. If you open up Google Scholar and search for observer design for state space and descriptor systems, these are the basic types of nonlinearities you are going to encounter. Okay, all of them are different. Some of them are actually special cases of others, but others are completely different. Okay, so if I make a Venn diagram, some of them overlap, some others don't overlap at all. Okay, and all of them are characterized by a specific parameter. So Lipschitz nonlinearities are the most common. I would dare say in all of the literature, 60% of the papers, or maybe 70% of the papers, assume Lipschitz nonlinearities. Okay, they are the easiest to derive because it's a bit easier to derive this parameter lambda here. Okay, so most of the literature, okay, has to study Lipschitz nonlinearities, but they are a bit more specialized. So there are other types of nonlinearities that are more general. And when I say more general, I mean that they basically cover a more general family of systems. Okay, so they can cover more cases of observers. So we have one-sided Lipschitz that are characterized by a parameter rho. We have generalized monotone, which are a bit stricter if I remember correctly. And then we have the much general category. I think these are the most commonly studied right now, which are quadratic and actually incremental quadratic that are characterized by matrix Q, which is symmetric. Okay. I think at the moment, the most common cases that are studied is Lipschitz and incremental quadratic, because incremental quadratic is actually a much general category. Okay. So different nonlinearities result in different LMIs in this observer. Of course, the problem here is trying to find out the parameters that I have here for the constraints. Lambda, rho, m, theta, q. I mean, we may assume that a nonlinearity is in this category, but we also need to derive this constraint matrix or constraint parameter. It's not easy or straightforward to do always. Okay, so this is a big problem. So most of the literature at the moment studies these categories of observers for these nonlinearities. So after searching a lot and a lot and a lot, we managed to actually identify a couple of other nonlinearities that are heavily understudied. Okay, I would dare say a couple, nor maybe not even a paper at all in these categories. These for me are very interesting categories. I believe this is where the state of the art in observer design lies, because by addressing observer design for these specific types of nonlinearities will heavily contribute to the field of observer design. These are very interesting. Some of them are very specialized, while others are actually much general. So we have a couple of specialized cases like passive one-sided Lipschitz or slope restricted or ellipsoidally Lipschitz. These are all special categories of Lipschitz. Especially locally Lipschitz has this parameter lambda here, which is a matrix that basically tells us that the Lipschitz property holds on a much more specialized or smaller domain. Okay, very interesting categories. And I also have a very big category. I would dare say I think almost no papers here, or maybe one paper. It's integral quadratic. You can understand that it's very general because basically it has an integral here. This is a very nice category. I believe it's much more difficult to derive an LMI for this case, but it will heavily contribute to the community at the moment if someone were to study these cases. So I believe in the future of observer, we should try and study observer design for these specific types of nonlinearities. I think most of them will appear in practice. They are much more difficult to analyze, and therefore any contributions here will be very welcome. Now, after covering, I think 70, 80 papers in the paper that we have, I think we covered pretty much all of the publications in the last 15 years or so. Okay, so we have some observations. One natural question for me is this: is it better to design an observer for a general nonlinearity or for a very specific one? My opinion is that both of these cases are very welcome and are very useful because, let me explain. If you design an observer for a very general category of nonlinearities, basically you will have an observer that works under most families of systems. So this is a very good thing. You want to go towards that direction. But if you choose to design an observer for a very, very specialized, very, very specific type of nonlinearity, well, this observer will not work under most systems. It will only work for a very special family of systems. But for this specific family, it will probably be the best observer. Okay. So as you can understand, both of these cases are very useful. One provides solution for general categories of systems, while the other provides solutions for a very specific category, but probably for this category, it's the best solution that you can find. Okay. So studying general and specific nonlinearities is both cool, both very useful for the literature, okay, and for the specific field. Now, another big problem, I think this is a very big problem for all types of studies. I mean, they also constantly battle over this in machine learning. Which observer is better? Now, this has a very simple answer. It doesn't have an answer, okay? Because it doesn't make sense to answer this, because when designing and when evaluating observers, there are many, many different design specifications. So let me think about it. One specification is how easy it is for the LMI to be feasible. Some observers may be very easily feasible. Others may be very strictly feasible. But the strict feasibility may lead to a much better observer, meaning that it may be very, may have a much better convergence rate. Okay. So the LMI feasibility or the convergence rate may be actually counteracting one another. Okay. So there may be uh, conditions that are actually difficult to achieve at the same time. The other condition is algebraic constraints, because in many LMIs and in many observer design problems, we usually have a collection of some algebraic conditions that need to be satisfied in order to derive the LMI. So again, some algebraic constraints are very, very easy to satisfy. Other algebraic constraints are very hard to satisfy, extremely hard to satisfy, actually. So again, this is an issue when having an LMI that is based, and its derivation is based on some algebraic constraints. And as I told you, the convergence rate is another condition for observer design. Some observers may have a good observer, I'm sorry, a very good convergence rate, but they may be hard to achieve. Uh, I'm talking about LMI feasibility, while others may be very slow, but generally very easy to have a conditional feasibility for their LMIs. So again, we have some conditions that are counteracting against one another. Okay, so it's very difficult to say which observer is better. There are many design constraints for each observer, and all should be taken into account. Okay, now there are also some other problems that we identified with the literature. One of them that I found very difficult to deal with is how we can identify the nonlinearity in the system. I have a very big difficulty in addressing this because I also did a couple of years a postdoc on observer design. I studied so many papers, and I saw that most papers did not comment on that. Now, they didn't comment either because they thought it was obvious, or maybe they weren't interested in it, or maybe because they didn't know about it. But for me, when watching series of differential equations that have nonlinear terms, sometimes it is not straightforward to understand what type of nonlinearity we have. In some cases, it is very easy. For example, trigonometric terms like sine and cosine are Lipschitz nonlinearities, but in other cases, it is not obvious. So this is an issue for me for the literature as it stands at the moment. And of course, another issue is that in many types of nonlinearities, like the ones that we mentioned below, where we have some sort of constraint, this sort of bound is not straightforward or not easy to derive. Okay, especially if you are working on specific simulation, deriving the Lipschitz constraint or the incremental quadratic matrix is not straightforward. Again, this is a topic that some papers don't care to address. I believe it is very important to address because otherwise you cannot have a proper simulation of the observer design. Okay, or even more so, a proper implementation of the observer design. Okay, so these are issues for me at the literature at the moment. I believe future papers will be able to address them, all of them correctly. Now, overall, this is a highly interesting topic. It is a very active field. Papers on observers are published every month. It's a very, very active field, and there are a lot open problems that we can address at the future. Okay. In our work, we mostly studied Leuenberger observers, which are very classic. But as you know, if you study observer, there are other observer types like functional observers or generalized dynamic observers. So overall, the literature is rich, and there are many, many open problems for the future. So if you take different types of nonlinearities and different type of observers like functional, Leuenberger, dynamic, generalized dynamic observers, you can have many different contributions both with respect to the type of observer and with respect to the type of nonlinearity, which has to do with the system type. So the field is very active and there are many, many, many open problems at the moment. Okay. I would welcome everybody to read the paper. It's in the description of the video. If you have any questions or want to discuss this, send me an email or simply write a comment below. Okay. So thank you very much and I'll see you in a future video.